This video is going to quickly overview the structures and the functioning of the human respiratory system. Now, as I go through these videos, obviously they can touch on various topics in more detail. This video right now is meant not for, say, majors in allied health, but more for, more of a general understanding of the respiratory system and some of the diseases that might affected. And so the respiratory system will not only touch on the bringing of air in and out of the lungs, but then also gas exchange, because obviously if the systems of the body, like the brain, need oxygen, need to get rid of their carbon dioxide, there has to be gas exchange between capillaries and the tissues, in addition to just getting air in and out of the lungs. So the respiratory system and its function actually have a number of steps, some of which, such as the external respiration, which is the gas exchange between blood and blood in the lungs and the air sacs in the lungs, and the internal respiration in tissues, which is the gas exchange there. They then involve the circulatory system. There aren't as many anatomical structures in the respiratory system. So the first structure is the nasal cavity, which then allows air in through the external nares or external nostril. We'll get to an internal nares in just a second. But there are a couple of bony plates known as conchae, which project into the nasal cavity. And that way, turbulence is created as incoming air, as I'll mention again in just a second. We have two senses of smell associated with the nasal cavity, the main olfactory system from the olfactory epithelium here. So when we smell odorants, they dissolve in mucus and trigger the olfactory neurons here. And there is also what's known as a vomeronasal organ. In humans, however, it does not work. And that's the situation in all higher primates. So for example, many mammals get input from pheromones from other members of their species, where humans don't rely on that sense to the same degree. And the main reason is that the vomeronasal system, which is the part of the respiratory system which perceives pheromones, and that's its main function, it no longer functions, although we still have the openings for it and those structures. And note that in mammals, breathing is so important. We need so much oxygen to maintain our high metabolism that a hard and soft palate separates the nasal cavity from the oral cavity. And that way we can continue to breathe even while we're eating. Once we bring air into the nasal cavity through the external nares, it can keep on going into the pharynx after passing through that opening, the internal nares. Now, the air we breathe may not be in the condition that we would like to introduce into our delicate air sacs. The simple squamous epithelia here is the most delicate tissue in our bodies. And so therefore, once we inhale air, those conchae, those bony plates, cause the air to swirl around. If there are there are germs or microbes or diesel particles, etc., in this air, these plates cause the air to swirl around. And so foreign particles will then get caught in mucus, and this mucus can be swept to the mouth and swallowed into the stomach, so that this doesn't come in contact with our delicate epithelia. But then also, a lot of the air that we breathe is cold in winter or dry, and the cells of our lungs are warm and moist. And if we brought cold, dry air to them, that would disrupt their homeostasis. And so as this air swirls around, in addition to filtering out microbes, diesel particles, dust, etc., then it also warms and humidifies the air prior to its introduction into the lungs. Once again, here is that hard palate, followed by the soft palate, the subject of the next video as well. And many animals lack this palate. So if you were to consider, say, a reptile or an amphibian, they have this one single opening, like a turtle or a frog. And so mammals with their higher oxygen needs needed to breathe constantly. And unlike, say, a turtle or a frog, they can't stop breathing just so that they can eat. And so while the nostrils empty into this big space here in this frog and this turtle, we mammals, we separate the oral from the nasal cavity. And this ensures then a more constant supply of oxygen, which we need with our large brains, our higher metabolism, etc. The hard palate is made of the maxillary and palatine bones. After the nasal cavity, the next structure is the pharynx. And the human pharynx is fascinating. There's so much going on during embryonic development. As an adult, however, not as much to mention. The part behind the nasal cavity is called the nasopharynx. The part behind the oral cavity is called the oropharynx. Above the larynx, that's called the laryngopharynx. We have some masses of lymphatic tissue here, the tonsils, 5 of them. We have one single adenoid tonsil or pharyngeal tonsil in back of the nasopharynx. But we have a pair of palatine tonsils and lingual tonsils, and that way this lymphatic tissue is strategically located to interact with microbes that we might encounter in air. And then the opening to the pharyngotympanic tube, which goes to the middle ear, so that air pressure on either side of the tympanum can be balanced. So if this is the eardrum, the middle ear is enclosed in space, and the air here would have air pressure. The problem with that is if we have air pressure here in the external ear and air pressure in the middle ear, then if the air pressure in the outside world changes, so for example, let's say we go up in altitude, or we go scuba diving, or we go on a plane, where the weather changes from sunny to rainy, etc., then this pressure would change. And if there's a different pressure on either side of the tympanum, it wouldn't be as free to vibrate, and we would not hear as well. So to guarantee that the air on this side of the eardrum is always the same pressure as the air on this side of the eardrum, we have a tube which goes into the nasopharynx of our throat, so that when, say, we go up in an airplane, not only is the new air with the new pressure here, but it can also go from our throat to the a pharynx and then a larynx. And the larynx is made of a bunch of cartilages which fuse in embryonic development to form this one solid structure. One of the important cartilages here is the epiglottis, which then separates the air. There's one portion where the airway and the foodway are shared. And the problem with that is if food ends up going into the airway, it could be lodged there and it could cause you to suffocate. And so therefore we want, even though there are 2 tubes in the throat, a trachea and an esophagus, we want food only to go in the esophagus, not into the airway with the larynx and the trachea. And so there is a piece of cartilage, the epiglottis, which closes over the opening to the larynx, which is known as the glottis, when we swallow. So part of the swallowing reflex is that the epiglottis will close, and that way food has no choice. It only goes into the esophagus. So even though, once again, we have these 2 airways, a larynx part of the airway and the esophagus part of the foodway, while air can pass into the larynx, any food will be blocked because this epiglottis would then close and direct a bolus of food then into the esophagus. And so thus, every time we swallow, there is the potential that we could choke on food, but the epiglottis prevents that by closing over the glottis. There are other cartilages of the larynx, the thyroid cartilage, the cricoid cartilage. The arytenoid cartilages have vocal cords attached to them. Here's the hyoid bone. So the larynx is a bit of a complex structure with a number of different components. When we pull on these cartilages, that then pulls on the vocal cords, and this then allows us to make sound. Now, sound is made by vibrations, and so it's the air being forced through the larynx that causes these vocal cords to vibrate. The more air that passes, the louder the sound. The more we pull on these cartilages with these muscles, the greater the tension, and that then changes the pitch. So just like, you know, a musical instrument, when you tighten the string, the pitch of the sound goes up. When we pull more tightly on these vocal cords, the pitch will increase. And so not only do we have, you know, natural variation in you know, the larynx and these vocal cords, but also during puberty in males, testosterone causes the vocal cords to lengthen and thicken. And just like on a musical instrument, the longer, thicker strings, they cause deeper notes. And so the same then explains the average difference in pitch in our voices after puberty between men and women. The hyoid bone surrounds the larynx. It is the one bone that doesn't contact any other. It's hanging from ligaments from the temporal bone. So the larynx would be behind it. And just like the larynx, when we were in developing as fetuses, we had all of these little pieces of cartilage from different pharyngeal arches, which then fused. Some fused to make the larynx, some fused to make the hyoid bone. So the hyoid bone's formation is actually more complex than you would imagine, coming from, you know, different pharyngeal arches of embryos, as, you know, all of the cartilage then fused to make solid structures. Now, as I had said, that as the air swirling around, there's foreign material that we would prefer didn't end up in the very delicate tissue of our lungs. And so we have cells along the nasal cavity and trachea which secrete mucus. So these are images of cells which could line, say, the trachea, and they have these little hairs known as cilia. All right. Now, this is not you know, human. This is a microorganism that has cilia, and the little hairs moving alongside along the cells would be about the same as what these human cells have. When mucus traps the diesel particles, the dust, the cigarette ash, the germs from people's coughs and sneezes, then the cilia sweep this up into the throat, where we swallow this into the stomach. Now, if you're thinking, you know, I'd prefer not to bring all of this gunk into my stomach, you know, I understand, but that's a far better choice than the lungs. The lungs are very delicate tissue. Meanwhile, the stomach is a big bag of acid. So that's a far better choice for where to bring this foreign material. So the nasal cavity, the trachea, in addition to having these ciliated cells, then have goblet cells. And here under the microscope, one can see, this is the large intestine, but the cells which are staining blue, here they're goblet cells which make mucus. That's what's been stained here. And so in the throat as well, we would then produce mucus which traps you know, foreign material, and that cilia would then sweep that mucus away from the lungs. So as air comes into the body, it comes from the nasal cavity through the pharynx, the nasopharynx, oropharynx, laryngopharynx, into the larynx, and then into the trachea. Um, the trachea will then divide here at this one spot called the carina. It's an irritable area sometimes when we cough. Coughs are initiated there. It then breaks into bronchi. So there are two primary bronchi which enter each lung. This then breaks into secondary bronchi, into tertiary bronchi, into then bronchioles. Bronchioles, go through several different classes of bronchioles before we get to the final category, which is the air sacs. So that's how air comes in, and air would then leave going in the opposite direction from the air sacs through the bronchioles, through the tertiary bronchi, the secondary bronchi, primary bronchi, the trachea, the larynx, the pharynx, the nasal cavity. Now, our respiratory passageways are surrounded by blood vessels. So these are the blood vessels of the lungs of a cat, which have been stained. And just one thing I always point out, right now, my left ventricle, in a heartbeat, it pumped about 70 milliliters of blood throughout the systems of my body, to my brain, my stomach, my arm, my leg, etc. My right ventricle also pumped 70 milliliters of blood in the last heartbeat, but that blood went to one place and one place only, the lungs. So the lungs get as much blood in each heartbeat as the rest of the body combined. So a lot of people don't appreciate that. So we have an enormous amount of blood, which then goes to the um, which goes to the lungs, and so therefore, there are blood vessels which hug these respiratory passageways, which get smaller and smaller. Arterioles and venules. Then they form the capillaries, which we'll be talking about in a second. The trachea and the bronchi, they have cartilage in them, as we can see, but they also have smooth muscle. Once we get into the bronchioles, they no longer have any cartilage. Now they just have the smooth muscle, and this smooth muscle can constrict and dilate. And so, if the smooth muscle of respiratory passageways constricts, we call that bronchoconstriction. Less air now goes that way. If this muscle relaxes, then this is bronchodilation, and more air goes that way. And then even the trachea and the bronchi, they can do some of this. Now the trachea and the bronchi, their cartilage prevents them from shutting completely. And the problem is then in the bronchioles, if one has asthma, if one inflames the bronchioles so that the walls are remodeled and become much thicker, then under those circumstances, when someone does bronchoconstriction, which everyone does a little of. I mean, if you go out into a cold, on a cold day and inhale cold air, or if you go into a smoky room, you will do some bronchoconstriction. But if your airways have been remodeled so that the bronchioles are much thicker, now they can completely close off the airway. The lungs are surrounded by what's called a serous membrane, just like the heart has a pericardium that surrounds it. The lungs have pleural membranes which surround them. And this, just like in the pericardium, this allows them to be able to move constantly without blisters and adhesions. So in the background here, you can see a cat's lungs being inflated and deflated with air. And so you need that the lobes of the lungs are now free to move without developing blisters and adhesions. So the fact that pleural membranes surround the lobes of the lung with a space, and the space can be filled with a lubricating fluid, this allows that. Now, we don't want regular air to be in this space because if it was, a lung would collapse. And so that's why if you had a puncture of the thoracic cavity and atmospheric air was introduced here, that would cause the lungs to collapse. So the space in between the pleural membranes and the lungs is important. It has to have air that's just a little bit lower in pressure than regular atmospheric air. So the trachea divides to make bronchi, primary bronchi, which enter the lungs, and a number of other things enter the lungs as well. Pulmonary arteries, which carry blue deoxygenated blood, pulmonary veins, which are leaving the lungs with red oxygenated blood, but then also nerves and lymphatic vessels, etc. And so there's this one section of the lungs called the hilus region, where a number of things enter and leave. Now we have two lungs, left and right, and they surround the heart in the thoracic cavity. They're separated into lobes. The right lung has 3 lobes because it has 2 fissures in it. The left lung just has 2 lobes with 1 fissure in it. And the left lung then also has a little space known as the cardiac notch, which appears here because the heart tilts to the left. 2/3 of the heart is to the left of the midline. So the left lung has to make space forward, and you can see that then in the cardiac notch. So as one goes down the throat, there are these 2 tubes, the trachea and the esophagus, the air tube and the food tube. And you can identify the trachea rather easily because it has these C-shaped rings of cartilage around it. So if you see 2 tubes in the throat and one has cartilage, that's the trachea. The bronchi then continue to have cartilage in them. And then if you were to look at the bronchi under the microscope, then one could then see that there would be patches of cartilage here and there. And so the cartilage would always keep the bronchi open. So in this video, there we go. So here's some cartilage. So you'll always see cartilage here. So the bronchi will not close completely, say, in an asthma attack the way the bronchioles will. And so here we continue to make mucus. There are goblet cells, as was pointed out here. So we're trying to trap foreign debris and then use cilia. And you can see that there are goblet cells here, which would make the mucus, and then ciliated cells, which could sweep this away from the delicate tissue of the lungs. The bronchi would get smaller and smaller as primary bronchi become secondary bronchi, which become tertiary bronchi, and then ultimately these then form the bronchioles. These are small respiratory passageways which no longer have cartilage. They would just have smooth muscle in their lining. And once again, they can undergo bronchoconstriction, which would let in less air, and bronchodilation, which would then let in more air. And the problem is then without the cartilage in an asthma patient, this could completely close. There's an interesting cell type that's in the bronchioles known as Clara cells. And so I have a video that goes through that. The bronchioles end in the last part of the respiratory tree, which are known as alveoli or air sacs. And each lung has about 150 million of them. And so when you think about lungs, in general, it's a big bag of these air sacs. And so these alveoli are kind of the functional unit of that. They are lined by these cells in tan. These are simple squamous epithelial cells, the thinnest cells that we have. Because air sacs are lined by these very thin cells, and because the capillaries alongside of them, remember how abundant blood vessels are in lungs, because they're lined by simple squamous epithelia, that's what lines capillaries, that gases can actually be exchanged between these two. So that's such an important point. I have two more videos that consider that with microscopic images. So once again, air does not mix with blood, right? So the air in the air sac never mixes with the blood in the capillary. But because they are so close to each other, that actually you can get an exchange between the two. If one were to look at the um, air sac, you can see how thin these cells are. Right, here we go. Previous video. So it's simple squamous epithelia. So the lungs are full of these air sacs. Now that's, perhaps an important image, because at the end I'll mention emphysema, and you'll see that these air sacs are missing. Um, and so here you see just simple squamous epithelia. You see how thin these cells are. And so this is the most delicate tissue that you have. This is why it's so important that you try to separate out debris and germs, et cetera, so that it doesn't, get introduced into this very delicate tissue. Well, not only is the air sac of the lungs composed of this very thin, delicate cell, but so too are the capillaries. So here you see the thin cells lining um, the air sac. But notice that blood vessels are then also lined by thin flat cells. You see how thin the cell is with its flat nucleus. So capillaries are lined by simple squamous epithelia, and air sacs are lined by simple squamous epithelia. And so there will be no direct exchange between here, this air sac, and this capillary. But because the cell which lines the air sac is so thin, and because the cell which lines the capillary is so thin, you can actually get oxygen going from the air sac into the capillary, and carbon dioxide going from the capillary back into the lung. This can be called the respiratory membrane, and this is the purpose of lungs, to get blood so close to the air that you can actually then have an exchange of gases, as oxygen is going this way, and carbon dioxide then goes in the opposite direction. Now, the thin cells are not the only cells in an air sac. There's also another type of cell which secretes something known as surfactant. Without surfactant, air sacs would tend to collapse. Tragically, premature infants can suffer from this, and actually tens of thousands of infants per year die in what's known as respiratory distress syndrome, where without sufficient surfactant, their air sacs can collapse and they can't breathe. So another cell type of these air sacs, known as the type 2 cells, secrete surfactant, which help to keep the air sacs open. Once again, a major risk to premature infants is that these type 2 cells might not be fully functional, making this surfactant. Now, the way that we breathe is that we change the volume of our thorax, our chest. And by changing the volume here, that changes the pressure. So just here, if pressure is the number of times that the ball hits the wall of the container, in the little container, it hits more. In the larger container, it hits less. So there is this inverse relationship between volume and pressure. When volume goes up, pressure goes down. When volume goes down, pressure goes up. And we take advantage of this. So salamanders, if you notice here, have to like suck air in and spit air out, by using throat muscles. But that's not a very good way to breathe. You would not be able to support your air needs, by sucking air in using your throat. And so therefore, we change the volume of our thorax. Now, reptiles and birds, like mammals, they have muscles between the ribs known as intercostals. So that was, an important development in amniovertebrates, where the ribs got long and touched the sternum, and that way the muscles between the ribs, known as intercostal muscles. These can now, change the volume of the thorax by pulling on the thoracic cage. Mammals then, because mammals need more oxygen than reptiles, mammals add one more muscle called the diaphragm, which then goes underneath the lungs. When the diaphragm is relaxed, the lungs are shorter. When the diaphragm contracts, it pushes down. Your guts hang out, but now your lungs get longer. And so the way that we bring air in and out of our lungs is by changing the volume of the thorax. If we want to inhale, we make our thorax bigger. And we do that because the muscles, the external intercostal muscles between the ribs, they contract, and that brings our rib cage out and up, so it increases its volume this way. And the diaphragm can contract, pushing the guts out, but making the lungs longer. That increases the volume this way. And then as the volume goes up, the pressure goes down. And if I increase the volume of my thorax, the pressure goes down. And if I open my mouth, the air just goes rushing in. So the air goes from an area of high pressure to low. So to inhale, we have the external intercostal muscles and the diaphragm contract. When we exhale at rest, these muscles simply relax. But if we are undergoing labored breathing, then we can have additional muscles contract to forcefully exhale, like our abdominal muscles and our internal intercostals. And so the way that we bring air in and out of our lungs is to change the volume of our thorax. Now, any additional points made, in discussing the respiratory system, I think start to leave what, perhaps a really quick general survey would cover, and then would get more into what, those who are studying anatomy and physiology, for example, in the say an allied health program would involve. And so one of the things, that would then follow is talking about then gas exchange. So in our lungs, we have a situation where now oxygen is going into the blood and carbon dioxide leaves. And so, we could talk about, the partial pressures which are affecting that. I talk about the hemoglobin of the red blood cells, which is binding the oxygen. That's certainly important. And then when this blood, say, gets to the brain, then the oxygen would go from the blood and the hemoglobin, and then go go into the brain tissue, so that brain cells could get oxygen. In respiration, the oxygen would contribute to then forming carbon dioxide, which builds up as a waste. And so now in the brain tissue, carbon dioxide would have to diffuse into the blood and then travel through the blood. Some travels as a gas, some bound to hemoglobin, and some travels as a molecule known as bicarbonate. And so once again, there would be a bit more that one could cover, such as, the respiratory centers of the brain, which are controlling respiration, etc. Just maybe 2 or 3 final points on the respiratory system. I have separate videos which deal with asthma. Asthma is a multifactorial trait. It's rather complex. And so I have a separate, set of videos which go through, the causes of asthma. But emphysema is literally referring to, quote, an empty chest, where those air sacs simply aren't there. For a while, if we lose air sacs, we can regenerate them. But after a while, the loss of air sacs can become permanent. And so if one were to compare healthy tissue with all of its air sacs to emphysema, an emphysema patient would have trouble moving air because the air sacs, which is where gas exchange occurs, they literally aren't there. They have been destroyed, whether this be through chronic exposure to cigarette smoke, to air pollution, to a variety uh, of things. Now, in exposure to a lot of contaminants, whether it be coal smoke, pollution, etc., while that mucociliary response tries very hard to remove debris from the lungs, we can, have air pollution and foreign particles reach the lung tissue. And so if you were to look at, the lung tissue of, say, someone who lives in a city compared to someone in more of a rural environment, one might notice that there are more foreign particles there. If one were to look at the lungs of a smoker or someone who worked in a coal mine, there could be just this enormous mass of foreign material, which would be contributing to the inflammation, which would worsen emphysema. But also, many of these particles could be toxic and be potential carcinogens. And so this is why smoking and exposure to air pollution would increase risk of lung cancer, throat cancer, and other cancers um, of the body. So there's a clear difference between the lungs of a smoker and those of non. And as mentioned with my videos on air pollution, um, when we look at the effects of air pollution, which in many parts of the world, especially those which don't have the Clean Air Act, which protects Americans to a large extent, as we look at the worsening effects of climate change, as heat waves, increase ozone formation and other air pollutants, then asthma attacks, and the incidence of heart attack and stroke as brought on by air pollution will increase. And so the respiratory system is functioning, and then also the things which harm the respiratory system, from smoking to air pollution to the various things which can trigger asthma, certainly very important topics today.